streaming. We got about 2 minutes left. Let me check on the streaming, make sure it's healthy. Yep, that's pretty good. We got about 14 people watching from YouTube. So the majority is still using YouTube instead of using Discord. That's interesting. One thing that the YouTube side can do that the other side or Discord cannot do is the sound of my desktop that cannot be heard on the Discord side. They can only be heard from the YouTube side. There are ways to kind of get around it too, but by default, that's kind of the case. All right, we got about 45 seconds to go. And now we got 9 people on YouTube, and let me check, around 8 people on Discord. All right, people are coming in, that's good. And at this point of time, it is really kind of important that you guys take notes, and also note, the time when I talk about a specific topic, and have a catalog of those dates as well as time, because there are probably occasions where you want to revisit a particular discussion, and having that catalog available to you makes it much easier to find the material in the videos, in the recordings of the lecture. And taking notes is going to be important too. I'm just suggesting, it's not required. You might need to kind of re-watch the video and kind of skip the parts where you think, I got this already, no problem. But take notes, when you're re-watching, because there are certain things you can probably better represent using a picture. Diagrams, tables, and stuff like that. So you might want to kind of spend some time to kind of find out, what is the best way to represent what we are learning in this class at this point. All right, so it is time, and I'm skipping to question number 3. All right, so here's question number 3. Assume C can access registers A, B, and C directly. What condition is true when execution continues at label X in the following TTP-ASM program? I forgot about to mention program, but that's basically what it is. All right, so label X, okay, let me just kind of magnify because I can't see it. There we go. All right, so here is label X. So the question is really kind of replicated by the comment here, which asks what condition is true here. So by the time we get to that specific point, what do we know for sure is going to be true? That's basically what the question is asking. So now the question really boils down to how do we get there? So there are 2 ways to get there. The first way to get there is the JZI instruction. So this can directly get to this point here. So now the question to go back is to ask, how can the Z flag be a 1 at the point of the JZI-X instruction? So that would be the first question to ask. And since the instruction immediately before JZI is an AND AA instruction, and we know that the AND AA instruction will affect the flags, or at least 2 of them, the Z flag as well as the S flag, the sign flag, can be affected by the AND AA instruction. So this is something that we talked about when we were doing the ABS lab, the absolute value lab. Because that was the trick to see if a register contains a negative integer by looking at the sign bit. So in this case, we are not interested in the sign bit. In this case, we're interested in the 0 bit, the Z bit over here. So the only way in order for AND AA to end up with the Z or the 0 bit being a 1 is when A itself is all zeros. So A basically as an 8-bit register has all 8 zeros. That's the only time that the Z flag is going to be set, and as a result, the JZI would go to the X label. So if A is 0, that means not A is true. So now we have narrowed down our choices to the second and also the fourth choice here. The other two is not going to work. Then the next question is, what about compares BC JZI to L1? So once again, we have a compare instruction. The compare instruction is basically a subtract instruction, except the difference is not stored anywhere. But it does still go through the motion of doing the subtraction. So in this case, we are performing a subtraction of B minus C. After the subtraction, it is also going to use a JZI, but this time it's not using a JZI to go to label X. It's using JZI to go to some label L1, which is not here. So the question is, if that is the case, how do we end up where the label X is located? The answer is, well, the Z flag has to be cleared. It has to be a 0. So now the question going back is to find out, okay, how can the Z flag be a 0 after a CMP BC instruction? And the only answer to that particular question is when B and C are not the same. So that means, when you look at this overall code, we get to the label X, where the comment is located, when A itself is false, or you can say A is 0, or when B and C are different. So the correct answer is going to be the fourth one, which is this one over here. So, so that's the explanation, of why that is the correct answer. And I'm going to submit just to make sure that the key is correct, because there are occasions where I forget, or I put in the wrong key. So in this case, let's see. Okay, did not answer. That one is correct. So, so are there any further questions about question number 3? Why the correct answer is not A or B does not equal to C? Okay, yeah, that's fine. That's good. All right. And there were some questions regarding what AND AA is doing. So that question really boils down to something that we already talked about when we did the lab of the absolute value. And also, it's a question that can also be answered by tracking what AND AA is going to do in terms of setting up the pathways within the processor. And it's going to have to go through the ALU, and then the ALU is going to, it's going to influence the Z flag as well as the sign flag, for every operation except for increment and decrement, because for those two, specifically, the flags register is not affected, and that is intentional. Any other questions about the previous lab before we move on to today's topic? All right, I'm not seeing any questions. There are 17 people on YouTube, so I do have to allow some additional time because YouTube has a little bit of a lag compared to Discord. All right, so it looks like there are no questions. So in that case, we're going to move on to today's topic. So today's topic, there are two things. One is, okay, let me kind of head out to the lab that we'll be doing tonight. So the lab that we're going to do tonight is, if you scroll down, too much. It's going to be parameters and return value. So that's what we will be talking about, is how do we return a value in a function, and how do we set up parameters, and how do we access parameters. So those are the questions that we want to answer in today's lecture. And the lab actually includes the instruction as well as points that you can also use for studying purposes. So the labs are not really just a one-time thing that you go through and you get some points. It's actually something that you can go back and study, use it as a resource for such studying purposes. All right, so let's go ahead and take a look at some examples. Let me see if I still have, nope, that's not what I'm looking for. I'm looking for a mouse pad. There we go. Here is mouse pad. And we're going to start a new sheet or new document here. And the first thing we'll do is to simply, look at a function from the perspective as a C function. So we'll uint 8 underscore t. So for the most part, until we have time to talk about big endian versus little endian, we are going to use unsigned 8-bit or signed 8-bit integers because the processor has registers that are only 8-bit wide. So in this case, I am going to implement a function. I'll just call the function 5, and all it does is to return a value of 5. Okay, so here is our function, and the question is, how do we do this? So as it turns out, most compilers, on most architectures, will simply dedicate a particular register as the register to contain the return value, especially when the return value is what we call a scalar, S-C-A-L-A-R. Okay, so a scalar is basically a value that can be contained within a register. So it can be a float, can be a double, can be an int, can be a char, can be a bool, in C++, and so on. But it's not going to be a structure. It's not going to be an object. It's not going to be an instance of a class. It's not going to be an array. So that's basically what a scalar is. And in this class, we're only concerned about returning scalars. We're not concerned about returning like an entire structure or an object, which you can do in C++, but it's awfully inefficient, at least with most implementation for most compilers. All right, so this is the C code, and we want to find out how this is going to be done in assembly language, or specifically in TTP ASM. So what I'm going to do now is I am commenting out the C code. So this way, when everything is done, I can actually just copy and paste this entire thing into the assembler, and it's going to assemble. So as usual, we use 5 as a label, to mark the entry point of the function. And then at some point, we're going to have to return back to the caller. So we're going to have the sequence of the instructions that returns to the caller, which is LD, BD, and increment the stack pointer, which is D, and then JMPB. So for those of you who are thinking, I have no idea what these 3 instructions are doing, that really means you might need to review the content, the material that we have already talked about, because we already talked about how to call and how to return, how to call a subroutine and how to return from a subroutine. That is in the, let me point out which module we are talking about here. So the module that talks about that is up here. It's calling and returning from subroutines, which also introduces the concept of a stack. So I certainly hope everybody has enough time to kind of review the material, because everything is really stacking up, no pun intended, in this class at this point of time. So being able to kind of keep up with the material, just making sure that we understand all of the material that has been introduced so far, that is crucial to get a reasonable score in the final exam. All right, so now what do we do about the return 5? Now this is just the code that is needed in order to return and continue execution in the caller, but it is not responsible to specify a return value. So in order to be able to specify the return value, we have to find out, okay, what is the convention? Which register is used to specify the return value? So in an Intel architecture, it's going to be register A, which can be EAX in a 32-bit version. It can also be, I cannot remember, I think it's HAX in the 64-bit version. I can be wrong about that one. I cannot remember the code name for the 64-bit version of the A register in the Intel architecture. Well, we don't have to worry about that here in Textoy processor, because we don't have 16-bit, 32-bit, or 64-bit version of that register. We only have the 8-bit version of the register. So we are still using register A. So in this case, just putting a value of 5 into register A is how we specify the return value. So we specify return value of 5, and then the rest of the code is to return and continue execution in caller. So this is where there can be a little bit of confusion, because in C and C++, those two things are combined into one single statement. So return 5 is going to do two things. One is to specify to return value, and then the second thing it's going to do is to continue execution in the caller. In assembly language, they're separated into two distinct phases. The first phase is to figure out what value we want to return, and then the second phase is to continue execution in the caller using the return address that is pushed on the stack by the caller. So that's how 5 is going to be implemented. So now we want to look at main in C first, and then we'll look at it in assembly language. So here's main, and in this case I have not talked about what to do with local variables, so we're not going to use local variables. And without local variables to store anything, I can do the call, and then I can do the return 0 from main immediately. So you guys might be thinking, so there's no way to check whether this code is working or not, right? Well, in C, you would not be able to tell whether the code is working or not, but in assembly language, using the tools that we already have, we actually do have a way to tell whether the program is working or not. So I just commented out the C++ code of main, and we're going to replace it with the TTP-ASM version of the same code. The first thing main needs to do, this part kind of depends on whether you want to initialize the stack pointer in main or you want to do it before main. Either way, it's fine, because main really is special. In the case of TTP-ASM, it's not really a subroutine, it's just an entry point for the entire program. That's basically what main is. It's just a label that marks the beginning or the starting point of the entire program. So, it really depends on how you want to structure your program or your code. So I'm going to put a NoOb here because execution always starts from the very beginning of the entire program. So it's always going to start with this NoOb in this case. And then the next thing I'll do is to LDID 0 to initialize the stack pointer. So this will basically move the stack pointer to 1 byte past the end of RAM. And the last location of RAM is location 255, but when I add 1 to it, it becomes 0. So if for those people who have the question of why are we initializing the stack pointer to be 1 byte past the end of RAM, once again, that discussion has already happened when we talked about calling and returning and the concept of the stack, so I would refer you back to that specific lecture. And then the next thing we'll do is to do a JMPI to main to continue execution in main. So this way I'm preserving the order of the definition of the subroutine. So main is defined after 5. Now, is that necessary? No, it's not necessary, because labels can be defined before or after the reference point. So main can be anywhere, and so can 5. Alright, so in main, the first thing we do is to make sure that we do halt at the very end, because otherwise it's going to execute all the NoOb instructions, all the 0 bytes, until it hits something that is not a 0, that is not a NoOb, that's not the opcode of NoOb. Then it's going to do something strange depending on what non-zero value is encountering in RAM. So we also always want to make sure that we end with a halt instruction here. So the next thing we need to do is simply to call 5 as a function, and the way to do that is to push the return address on the stack first, and then we do a jump to 5, and that's how we're going to do it. So we are going to have to use a label to tell us where it is supposed to return to. So we're going to use register A here, because the only thing we can use to store into RAM is a register. Okay, so you don't really have a way to push anything other than a register on the stack. So we're going to say return to main, since there's only one point here, so I can just use this name as a label, and we'll define it later. And then the next thing we need to do is to decrement the stack pointer, and then do stda to basically push the return address. So at this point, we would have pushed the return to main label onto the stack. Now that the return address is on the stack, we can now continue execution in the subroutine, which is a JMP I to 5. And when it does return, to this point, to the point right after, it's just going to be halting, and that's the entire program. All right, so I'm just going to take pause here and see if there are any questions about the program, both the one that is written in C, which is commented out, and the implementation in assembly language. All right, so, oh, okay, there we go. So Philip is typing. Oh, okay, cool. So far, so good. All right, so this is what I claim the program is going to do. Remember what I said a little bit earlier? If you are to write this program in C just like this, you would have no idea what 5 is actually returning, because we are not storing the return value of 5 into a variable or in any way using it for anything. So there's no way for us to really know what 5 is returning. But in assembly language, we actually do have a way to tell what it is returning, because by the time we get to the halt instruction, we can examine what register A has, because after all, we understand that register A is the register that we use for returning a value. So by the time we get to the halt instruction, we can just check the value in register A and just make sure it is 5. Okay? So to test this program, there are two ways to do it. I'm going to use both ways. The first one is to run it in interactive GUI mode, which is okay for programs of this type of simplicity. But generally speaking, it's not a very good approach, because you can't really see what is going on in between until we get to the halt instruction. So that's very good. I like how you guys are already here. This is a good use of the resources. I mean, there are very few other classes where they use the professor would use a spreadsheet that you can use to. Oh, okay, there we go. We have an unresolved reference. Okay, that's because I forgot to define the label of return to main. So let me fix that first in the actual program. All right, let me turn on the line numbers, and you guys can help me figure out where between which two lines I should insert the definition of return to main. In other words, when 5 is done, where should I go back to in main to continue execution? So we got Dylan typing, very good. And we got Omer also answering between line 10 and 11. And I'll answer that question that Dylan asked in just a little bit, but right now we're going to be focusing on that question. Where do we put the definition of return to main, which is a bookmark to indicate when 5 is done, where is it supposed to go? 25. And that would be correct. It'll be between line 24 and line 25, because this assembler is a little bit too simple. You cannot define a label and also have an instruction on the same line, so the definition of the label has to be on its own line. But that's okay, because that's how we're going to do it. Okay, so when the subroutine is done, this JMPB will eventually end up on line 26, which is proper because that is the continuation. Even though there's nothing to do, that's basically where we want the subroutine to continue after it is done. All right, very good. So let me get back to Dylan's question of just curious, what would other professors use instead of TTP? They would use the Intel architecture, which is one of the most popular architecture, at least in the past. So it's well known. There are assemblers, there are compilers, and so on and so forth for that processor. I do not like that processor for instruction purposes, because it supports a lot of different addressing modes, and it gives you instructions just for pushing and popping, calling and returning. So it is convenient, but it is also hiding a lot of the details that we are supposed to understand when we write programs in assembly. So that's why I do not like that processor, for instructional use. And then the other one is most compilers like GCC can target the x86 architecture. So sometimes when people do not know how to implement a program in assembly language for the x86, they just use a compiler and have the compiler to output in assembly language. So not so easy with the TTP ASM. I mean, if you write a C compiler that cranks out TTP ASM code in the back end, I would say you probably understand the material really, really well enough to do that. So I actually wouldn't mind that for the person who's actually writing the C compiler for TTP. But the x86 architecture is so prolific, it's just everywhere. There are tons of tools already available, to that processor. So getting a compiler to crank out x86 assembly language code is like easy. So I don't. That's another reason why I do not use the x86 architecture. Anyway, so now that we have this program fixed, let's go ahead and give it a try. Okay, so we go back to the source tab and repaste the entire program. And this time we should not have that error. Oh, great. So we don't have any error in this case. So as usual, we go to the RAM file, we go to File, and then we go to Download CSV. And this time I'm going to call this one 5. Okay, so there we go. And then we'll go ahead and run it in Logisim. I don't have a running instance of Logisim, so give me a moment here to start up one. There we go. Alright, so now that we got the processor loaded into Logisim, we just have to load the program into RAM. So right click, go to load image, and then we just have to find the file that we saved it to, which I think is 5.csv. So it's right here. Click open. So now we got the program, and as I said, if you really don't care what is happening in between and you trust that the program is going to reach the halt instruction, you can just go ahead and run it and just keep an eye on register A until at the end of the execution. So we just go to simulate, we enable the ticks so that you don't have to keep clicking on that clock pin, and now it's done. So let's go ahead and stop all the ticking. And then we'll take a look at register A and see that it is 5. So 101 in base 2 is indeed 5 in decimal. So this is kind of cool. We can also see that register D is back to 0, which means the stack is empty at this point, which is important. Okay, you have to make sure that the stack is quote unquote balanced when the program is done. So that's the the basic that's the basics of how you return a value from a subroutine. All you have to do is to put the value that you're supposed to return into register A before you return from the callee or the subroutine or the function back to its caller. Alright, so I'm gonna pause and see if there are any questions. It's not a memory leak if it's not balanced, but it means the program is not implemented correctly. Because if the program is implemented correctly, you should get back to location 0, or the stack pointer should point back to location 0. So even if the program doesn't crash and seems to be doing everything that it's supposed to do, if the stack pointer is not balanced, I will take points off, because that to me is means the program was not implemented correctly. All right. Any other questions before we move on to parameters? In other words, where are we going to store the parameters and what are we going to do about those parameters? All right. All right, so Dylan has a question or a point. I'm going to wait a little bit. All right, so what would this program have to look like for the stack pointer to be unbalanced? This one, not so easy. Oh, okay, I find a way. So the program would still get back to the hold instruction if this increment D was not here. In other words, if I comment out this increment D, the program would still quote unquote seems to be running correctly because it does return to the caller. But then the stack pointer would be pointing to location 255 by the time we get to the hold instruction. So that's one way to quote unquote mess up the program so that the stack is no longer balanced. So that's that's one way to do it. Any other questions before we move on to parameters? All right, Eric has a question or point. If anyone feels comfortable, you can use the voice channel on Discord as well. All right. If we didn't pop off the stack, would the only problem be that eventually we might run out of stack memory? No, that's not the only problem. In this specific program, it's not going to be a big problem because the stack pointer is not correct anymore. If you have a program where main itself also has its own local variables, or you have a recursive call or something along that line, not cleaning up the stack means the program is going to get to the wrong place. It's going to go to La La Land in some cases. So I can illustrate all of that crazy stuff later on. Um, you know, but the point is, if you don't pop, if you don't increment the stack pointer, if you don't deallocate, from the stack properly, it's not just a problem of using additional bytes. The program would actually behave incorrectly in general. In this case, the program is so simple it doesn't make much difference. All right. So Eric is typing. I'm gonna wait. All right, so if we had nested function calls, we might not return to the correct location. That is correct. Okay, so if you have a nested call, then we'll be in trouble because the stack is at the wrong place. The stack pointer is at the wrong place. That is correct. All right, excellent. So let's see what else we can do with just return values. So we're going to take a look at another program. And let's see, go to File, New. All right, so I'm debating with myself whether to use VI or not, because I keep trying to use the VI keystrokes, and of course, this is not, mouse pad is not VI, and it doesn't work. I think I'm gonna go switch to VI just because to me that's a whole lot more efficient. To most people, VI is really kind of difficult to use, but if you have been using it for like 20 years, not only do you become proficient at it, you become not proficient with anything else. So here we go. All right, so here we have another program, and we'll just okay, so we'll call this program 12. Okay, TWELVE.C. Okay, so I'm looking at the C version first, and I will give you a program that actually compiles in C++. So we'll have a pound include stdint, which is standard integer.h. This is where uint8 _t is defined. So we'll go ahead and do the same thing here, uint8 underscore t, but instead of calling the subroutine 5, we'll call it Johnny. If you have paid attention in the previous class, you will understand the association between the value 5 and the name Johnny. And then the second one, we'll call it Ryan, and it's going to return a value of 7. This one is a little bit more obscure because 7 of 9 is a Borg as a character in Star Trek Voyager. And Ryan is the last name of the actress who played 7 of 9. So that's why it's a little bit more obscure with this one. And then in main, we are going to, oh, wait, okay, so now we have uint8 underscore t12, which doesn't take any parameters, but it does do something that's kind of interesting. So I am basically using only the material that we have talked about, which is calling and returning from a subroutine and how we specify the return value, to basically as a illustration of writing a program like this. So main is going to call 12 because I don't have local variables, so it can only call, but it cannot store anything. All right, so now we have this program, and the question is, how do we implement this program in assembly? So before we do that, we might want to just compile this program to make sure that it does compile and it does do what it's supposed to do, which is not possible to see because we cannot see whether a subroutine is returning the correct value in C without storing that into anything. The only thing we can do, this is not something that we can translate into assembly, but what we can do is we can printf this one. Okay, so we can printf. This is it's just going to be an 8-bit char. So let me see how we can specify that. Well, we can cast it to an unsigned before we print it. There we go. So I'm doing all of this stuff here. This stuff here, with the printf, is only to print it so that we can see that it's doing it correctly. But to do that, we also need to include standard in standard IO. There we go, standard input output.h. All right, so let's go ahead and recompile the program and run the program, and it prints 12 as expected, right? Okay, so now what we want to do is to look at this program and see how we can translate that into TTP-ASM. So now we look at 12 again, .c. Actually, I'm going to do this. I will copy 12.c into 12 twelve.ttp-asm, and then we can edit TTP-ASM. All right, now the nice thing about using VI, is I have the syntax highlighting tool. Anything that looks like this, which is, I guess you can call it salmon as the background color, that means it is incorrect. That's because these are all C code. It's not in assembly code. So I'm just going to comment out everything by inserting the /a// before all the lines. And oh, okay, that's not good. Let me do that one more time. We replace all the beginning of a line with / space, and press the enter key. There we go. All right. So now everything is good because we don't see that salmon background color anymore. Now we do the usual typical thing, which is NoOb as the first instruction, because you need the NoOb in order to use the tool for trace analysis. So that's why NoOb is going to be the first one. And then as usual, we initialize the stack pointer to 0 and then do a JMP-I to main. And then we define Johnny. Okay, so Johnny is just returning a value of 5, LDIA 5. And then we have the 3 instructions to return to the caller. LDBD, because the return address is pointed to by the stack pointer. And then we increment D because that location is no longer in use. We're going to deallocate that location on the stack. And then JMPB, which is using whatever value is in register B to continue execution. Basically, all it does is to copy register B to the program counter. Alright, so now we can just copy this, 5 lines to copy, and then paste it over here. Oh, not there, there. And then replace the name of the subroutine, which is just a label to Ryan, and then return the value of 7 instead of 5. Alright. So now we have 12. Okay, so same as usual. We have TWELVE as the entry point, and then we know the exit point is going to be the same 3 instructions anyway. So we're going to put it over here. So the big question now is, what are we going to do to call Johnny and then call Ryan and then add the return values of those two together? So we're going to focus on the calling first, okay? Because that's going to be the most important part. Is we have to call Johnny and then we have to call Ryan. So to do that, we have to use LDI to store to basically we have to push the return value. I mean, take that back. I take that back. We have to store the return address. Okay, we have to push the return address before calling. So it's going to be I'll make this really long so that it's clear which what return address we are talking about. So this is Johnny returns to 12. Okay, that's a pretty long name, but it does kind of self-document and tell you what that label is trying to do. So we load A with that label, decrement D to push, and then we have a stda. So this is to push return address on the stack, and then we do a JMPI to the first subroutine, which is Johnny. And when it comes back, this is where we want to return to. This is where we want Johnny to return to after the call. So the name Johnny returns to 12 is going to be defined here. And obviously, we're going to have to kind of copy and paste this code to call Ryan. So we have line 32 to line 36. Copy to where we are now, and then we just have to make sure that we replace Johnny with Ryan. So that would be from line 39 to line 43. Replace Johnny, John Johnnny, with Ryan. All right, so there we go. All right. And now you can start to see why I like VI, because it just gives me quick and easy way to replace certain things within a range of line numbers and stuff like that. So it's kind of handy. All right. So now we have the 2 calls, and after the first call, in other words, on line 37, register A would have the return value of Johnny. On line 44, the same register, which is register A, is going to have the return value of Ryan. Do you guys see a problem here? Because we are supposed to add the return value of Johnny to the return value of Ryan, but both are going to be stored in register A. So how are we going to solve this problem? Okay, first of all, are we seeing the problem? Put each value in a separate register. Well, that would be a good idea, except when you call a subroutine, the subroutine can mess up every single register that you have. In other words, there's no telling what kind of register Ryan will need in order to get his job done. And Eric is correct. We use the stack. All right. So we can kind of see, even though I have only introduced a few, concepts, those concepts, when you apply those concepts in different ways, they can do all kinds of tricks. Okay. So what we are going to do here is right here at this point, register A has the return value of Johnny. I already know register A is going to be messed up, after this. So what I do is I push it on the stack. I save it on the stack. So to do that, we just have a decrement D, to allocate that 1 byte on the stack, and an stda. So we are pushing the return value of Johnny on the stack. So after that, okay, Ryan as a subroutine, as a function, can mess up register A all it wants. Okay, it doesn't matter because we have already saved the return value of Johnny on the stack, and we can retrieve it later on, right? So at this point, right after Ryan returns to 12, so at this point, register A is the return value of Ryan. Okay, because we just returned from Ryan. Where D is pointing to, okay, that is the return value of Johnny. And we're supposed to add those two together. So the first thing that some people would use is, oh, we can just do something like that, right? That doesn't work, okay, because dereferencing D using an asterisk, that is a C++ operator. The assembly language does not support that. And then somebody's going to remember, oh, there's that LD instruction. Seems like when we put parentheses around a register, that means dereferencing. So instead of doing this, maybe we can just, oh, there we go. Maybe we can just do this. Well, the syntax highlighter says, nope, that is not supported either. It's not supported not because the language does not support it. It's not supported because there are no such pathways in the processor. There's no way you can actually connect the D port of RAM to one of the two inputs into the ALU. That path does not exist. So that is why we cannot do something like this, even though it seems like, hey, it would be kind of nice if we can do that. Well, I'm forcing you guys to think about it and go like, no, we only have very primitive instructions to begin with, so you cannot do it like this. So if this is not possible, how are we going to solve the problem? Well, the way we're going to solve the problem is we're going to pop that return value of Johnny into a separate register first. So we're going to pop it into, say, register B or register C. Both of those are available at this point. So we're going to do an LD first. So LD, okay, I'm just going to pick register C here. So this is how we pop a byte from the stack. Okay, so I'll just comment here and say pop return value of Johnny into register B. So at that point, now we have register A being the return value of Ryan. We have register B being the return value of Johnny. And we know add can add the values of two registers. I mean, that's the only thing it knows how to do, is to add the values of two registers. So now we can do an add AB, which adds the value of B to A, which is handy because we want A to specify the sum anyway as a return value. So this basically kills two birds with one stone. So we are good here. Alright, so with all of this done, we can now specify what goes into main. So main is here. And we need a halt instruction as the last instruction. So now we can set up the call not to Ryan, not to Johnny, but to 12. Okay, so we're going to do the usual stuff. Okay, LDIA with 12 returns to main. Decrement D, stda, JMPI to 12, TWELVE, and define the label here as TWELVE returns to main. And that should do it, right? Oh, you're right. Christopher is correct because I chose to use register C to pop the return value of Johnny. So it should be add AC and not add AB. Thank you. Very good. Alright, so I claim that this program is going to get the job done. Are you guys going to trust me when I say that? All right, so Omer is typing, so I'm just going to set up everything so it'll be ready to go as soon as possible. Could we get a copy of this once I'm finished? It's a little hard to see piecemeal. Absolutely. So I'm going to do I will do one thing that's even better than that. Okay, so let me change back to the folder where I need to go. So I will push folder to Documents, CISP310, River Spider. All right, so now I can use my script. The script is just submit, and the file that contains the source code is /temp/ what is this again? 12 twelve.ttpsm. So this saves me, a bunch of steps that I could have done manually. So for those of you who do not want to spend the time to set up, River Spider, you can always kind of do this manually, which is what I have done for years until I finally got so sick and tired of having to navigate in Google Sheet, back to the command line, blah 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 blah. So it's not like it's not. I mean, it's not like it's super complicated. It's just with this tool, it's it's a whole lot easier. So what are we gonna do? Well, we're gonna go to analysis, okay, because that is what the tool does. So for those of you who want to have a copy of this program, this is where you want to make a copy. Just go to File, and then go to, what is it again? Make a copy. There we go. So go to File, go to Make a Copy. Then not only are you making a copy of the assembler, you are making of the assembler when the source code is what you want to capture, and also when analysis has exactly the trace of executing this program. So that can be handy, and you don't have to rush, okay? Because I'm gonna yak a little bit before we switch to the next program. So you do have a little bit of time before I switch gear to specify parameters. All right. So the first thing is we double check, make sure the register D is balanced. Okay, that's good. And then we also want to make sure register A, which is responsible to store the return value, has 12 in it, right? And that's exactly what we saw. Okay, register A has a content of 0C in hexadecimal, which is 12 in decimal. And then the third thing, which is also really kind of important, is to make sure that the last instruction that we get to is indeed the halt instruction that we had earlier. So in order to check that, we have to go back to the Assemble tab. This is why I put the Assemble tab and the Analysis tab right next to each other, because they really work well together. So we go to the Assemble tab, we kind of scroll down until we get to the halt instruction, which is here. And we can see the halt instruction does have an address of 29 in hexadecimal. So that means, by looking at the Analysis tab, we did stop at the right place. The stack pointer is right because it is back to 0, 0. The stack is now empty. And on top of that, register A, the last time we update register A, is to put a value of 12 into register A, and that is exactly what the subroutine or the function 12 is supposed to return. So this is how I can just really kind of double check, make sure everything is working in this program. So I'm going to pause here and see if you guys have any questions. If not, then we'll move on to talk about parameters. And also, if you want to make a copy, now would be a good time because I'm kind of done talking about this program already. So just go to File and then go to Make a Copy. And for those of you who are thinking, maybe just not out loud, of where am I supposed to find this stuff? I'm going to put it into the text channel, but you're supposed to know where to find this stuff already at this point of the class. There we go. All right, so is the stack stored in RAM in Logisim? Yes. So RAM is storing both the program itself. Remember another Johnny. Remember John von Neumann? John von Neumann is the one who invented, guess what? The von Neumann architecture. And the reason or the main driving force behind that is to be able to store instructions in RAM. But the stack is also in RAM because it is representing the data that we are trying to process. It's a very special kind of memory. It's a special kind of data, but nonetheless, it is still just data. So there you go. Oh, thank you, Omer. He already made a copy of the source code, and then Bernard is typing. So I'm gonna wait until Bernard is done. So you are using the backend of the RAM to prevent any instruction from being overwritten. Yeah, that's sort of the idea. But when you have a program that runs away and it's recursive, it can potentially use more and more locations in the on the stack until it runs into the code. This particular architecture is very simple, so there's no protection against it. So you basically just end up with a stack corrupting instructions that you're supposed to execute, and things would just kind of go really haywire, when that happens. So there's that. All right. So any other questions before we move on? I'm just setting up here, but if you do have questions, you can kind of ask in the text channel. All right. So it looks like we do not have any questions. All right. So if there are no questions, I'm just doing some quick counting here. So I think I got about 16 people-ish, on Discord and about 16 people on YouTube. The class, technically speaking, still has 50 people. So 50 minus 32 is definitely not 0. So the question is, where are the 18 people right now? All right, but that's not a question that I really need to answer. So we'll just kind of skip that question. All right, so now we're going to look at parameters. Okay, parameters are kind of interesting. Okay, it's very useful, right? Because this is how the caller and the function communicate with each other. So we'll go take a look at a very simple, function, and you're going to go like, oh, that doesn't seem to be useful at all, and that would be the whole point. So it's going to be called parameter, and we'll look at the C version first, and then we'll look at the assembly language implementation. So there we go. And the C version is going to use uint8_t, okay, and it's going to be a function called, we'll just call it clone, okay. It takes one single parameter, which I will call x, and that's what it's going to return. Not very useful, is it? Well, that's okay, because we are only using this to illustrate how it is done, right? So in main, we're just going to go ahead and call clone, and with a constant as a parameter. In this case, we'll try 42. Okay, 42 is also kind of special to geeks and nerds, so we'll use 42 as a number to pass to clone. All right, so this program obviously is not going to do anything particularly useful nor spectacular, but it does help us, understand, how it's going to be done in assembly language. So before I move on to talk about the assembly language implementation, do we have any questions about the C code here? All right, there are no questions. Okay. All right, so let's go ahead and convert this program into assembly code. So we'll do a CP and take the C code into TTP ASM, and then we'll edit the TTP param1.ttp ASM. There we go. Obviously, everything is no good because this is not in TTP ASM code. So once again, we replace all the beginning of a line with / in the space. And now we have commented out the entire thing, except we can still see it, right? So that's nice. We have NoOb, we have LDID to 0 with 0, JMPI to main, and then main is right here, and a halt right after main just to make sure that we do stop. And main now has to call clone, so we kind of know the the calling part is easy, right? So let's take care of that first. So to call, we have LDIA with clone return to main, decrement D to reserve 1 byte on the stack, and then we put the return address onto that location that we have just reserved, JMPI to clone. So that's kind of, and then when we return, we want to return here, which is clone return to main. Is right here. Okay, so that seems pretty easy, except, we haven't really, dealt with how do we pass parameters. So passing parameters is a way for the caller, which in this case is main, to communicate with the function that we are calling. And so there are only a few ways that we can think about. The first one is, let's just use some global variables to do this. Okay, use global variables as a way for a caller to communicate with a subroutine. That's just a really bad idea. Okay, for many reasons. Okay, at this point, I'm just going to say to this class, to all of you, anytime you want to use a global variable, you really need to think, is that necessary? Okay, the only kind of global thing that I would use in any program is going to be constants. Okay, so constants, you can make global ones like pi or number of entries in an array or something along that line. Maybe those stuff can be global, but as far as variables are concerned, just not a very good idea to have global variables. Static variables within a subroutine, so I'm guessing what Bernard is referring to are static local variables. Those are very special. They're very special occasions where you would need a static variable within a subroutine, within a function. Most of the time, not a good idea. Okay, there are very specific reasons why you might want to consider the use of static variables. Generally speaking, instead of using static local variables, you probably should be using classes, where you have static members in a class. So those members are not specific to an object. It is actually specific to the class itself. So in an object-oriented program, I would use a class member to basically do what usually you would use a static variable for. So there is that. All right. So global variables are out. Okay. Second thing. Okay. Maybe we should use registers. Well, registers are nice. Okay. If you have an unlimited number of registers, sure, why not, right? Use registers to store parameters because they are easy to specify from the perspective of the caller, and they're also easy to get to from the perspective of the function. There's only one problem. Well, on most architectures, the number of registers is very limited. The TTP only has 4 registers, and each one is only 1 byte wide. Okay, so we are not really talking about a lot of locations where you can pass a lot of different kinds of information. Even with the x86 architecture, I think there are only like 16 registers. Each one is really wide, right? Each one is 64-bit wide, but you're only still looking at 16 registers. So that may not be a good idea because it's very limited. So what we're going to use is, once again, use the stack. Okay, so we're going to use the stack to pass parameters. And the way we do that is we push the parameter before we push the return address. So now, to call clone properly, we're going to push the parameter first, which is 42. And every time we push, we have to decrement D and then store to where D is pointing to the actual thing that you want to push. So this is pushing argument 42 on the stack. And then we push the return address, and then we call or continue execution at clone. Okay, so you might want to kind of track what is on the stack, right? So I'm going to help you with putting some comments here that is kind of um, a certain representation of what is on the stack. So I'm going to use square brackets to highlight what the stack pointer is pointing to. So right now the stack pointer is pointing to a location on the stack that has the content of 42. And then at this point, 42 is no longer being pointed to by the stack pointer. Instead, it is a byte that has the return address that we just push on the stack. So obviously in this notation, whatever is on the left hand side is at a higher memory address. Whatever is on the right hand side has a lower memory address. So that's how I'm using this method to kind of show you semi-graphically what is on the stack. All right, so now, okay, let me pause first. Okay, let me pause and make sure that we all understand what is going on here. We push 42, which is the argument on the stack, and then we push the return address on the stack. This specific order has a reason, but it's also just seen as a convention for most compilers. Do we have any questions? All right, maybe not. So what we'll do is now we try to look at things from the perspective of clone. All right, so we'll go ahead and write the clone implementation here. So this is clone, and we know it's a subroutine, so we might as well just kind of start with the end, which is LDB D, increment D, and then JMPB. Okay, so that's the return, returning control or continuing execution to the caller. So now the question is, how do we get back to X? So there are several ways to do this, okay? But no matter what you do, the first thing you need to do is to find out what is on the stack. So the way I specify what is on the stack right now is I know the stack pointer is pointing to the return address. And above 1 byte above the return address is the parameter X. So someone may be asking, but Tech, we already know this X is actually just 42, and then the return address has the label of clone return to main. So why do I use why don't I use 42 and clone return to main over here? Well, the reason why that is the case is I don't know who is calling clone. From the perspective of clone, it doesn't know who is calling it. The only thing it does know is whoever the caller is understands the protocol, understands the standard, which means push the argument first, and then push the return address. So that's why from the perspective of the function being called, this is all I can tell is the stack pointer is pointing directly to the return address, and the argument is 1 byte above it. All right, so if that is the case, we can just do something like this, right? Increment D, because now D points to X, and then we do a LDAD, and then decrement D again, so that it's getting back to its normal location, and everything should be good. Well, this code is going to, it would seem to work. Okay, that's the best way that I can use to describe it. It would seem to work, but it's not going to work in general in the general architecture. And somebody's going to ask, but why? Why is this not going to work? So to understand that, okay, what you need to do, what you need to imagine is there are gremlins, in the processor. Okay, so I'm gonna post a picture of gremlin, a gremlin. So gremlin. There we go. All right, so you can kind of imagine that in the processor, there are gremlins, okay? And these gremlins are just kind of doing stuff, doing destructive stuff, okay? But they respect one rule, okay? There's one rule that they always, play by, which is they will only mess up stuff, that is below where the stack pointer or register D is pointing to. Anything that is above or at where the stack pointer is pointing to, these gremlins we're just going to leave it alone because that's the rule, okay? So that's why we don't want to do something like this, because the moment you increment register D, the return address is not safe anymore, because right after you increment D, one of these gremlins can go to that location where the return address is located and mess it up. All right, so even though later on we decrement D back to where it's supposed to be, the damage has been done already. So when we perform the LDBD instruction, which is supposed to get the return address, we're going to get something that's corrupted. So by the time we get to the JMPB instruction, we'll be jumping to some location that is not the return address. So that is why we cannot do something like this. Okay, bad idea. Okay, it looks like it's going to work, but it's not going to work. And some people would try this out, knowing how I would have done. What I would have done is I'm going to try this out anyway, and people will complain to me and go like, "But Tack, look at this. I've done this like 20 bazillion times, and it's still working. So what you said is not true." Well, that is actually kind of true because this processor TTP does not have any interrupt capability. Um, and that's a whole different topic, okay? But I'm just going to say why the symptoms may not happen, in certain architectures. Okay, so in this specific architecture, because we do not have interrupts, so doing something like this, the program is actually going to quote unquote work all the time. But if someone turn in this kind of solution to me, I will count it as wrong. Okay, because I'm not teaching you guys to specifically only program in TTP or on an architecture that has no interrupts. I'm trying to teach you guys to write a program that is always safe and always behaving correctly regardless of what architecture you're going to use. So from that perspective, this code is wrong. Okay, so even though it might give you the result that is reliably correct all the time, but it is by itself wrong. Okay, so if that is the case, what are we supposed to do? Well, this is what we're going to, this is something we can do is we can just make a copy. So I'm copying register D to register C. So right after this point, now I can just use register C instead of register D to do all the dirty work. So when you look at this, look at it from this perspective, okay, so I'm just going to comment here. C is D. This is an assignment. At this point, C is, this is a comparison. I'm trying to, oh, okay, wait, hold on a second. I have a better way to say this. So after the increment C, whatever C is pointing to is X. So C is a pointer pointing to argument X on the stack, which means this instruction is going to say A is the argument X, which is mission accomplished, right? Look at line 6. That's what we're supposed to do. We're supposed to return just the value of the parameter X, and that's going to get the job done. Line 12 is going to get the job done. And then lines 13, 14, and 15, those are the usual stuff that we do when we return from a subroutine. So we're not going to explain that any further at this point. So I'm going to pause here and see if you guys can have any questions. Okay. I mean, I can even kind of give you a picture of what this looks like. So X is on the stack. Register D, which is the stack pointer, is pointing to our return address. But at the same time, we also have an alias. Okay, so this is my approximation of a pointer, because register C is going to point to the same location. And then with the increment here, okay, so let me copy this. With the increment C, then C is no longer pointing to return address. It's going to point to the location 1 byte past the return address, which means C is now pointing to the value of our argument. So that's kind of why the next instruction is going to work, because we are just going to copy whatever C is pointing to register A, which accomplishes what the C code is attempting to do. All right. So do we have any questions about this program? Other than, but I want to see it work. All good? All right. So let's go ahead and see whether it works or not. Okay. And to do that, I have my nice little tool. So I can just do this. All right. So now, if you make a copy of the same spreadsheet, this time it's going to be for param 1. So that's kind of nice, right? If you're already here, hey, just go to File, make a copy again, call it, save it under a different name for param 1, and now you have the other program. Now the indentation, unfortunately, in source is going to be kind of, oh no, it's still correct. That's fine. Okay, so this is really nice. Okay, it's nicer than I thought it would be, which is obviously not a problem. All right, so what we can see here, there are several things we want to see is how do we get the 42, right? So you can follow the instructions here, line by line, instruction by instruction. You can find out when we push the 42 on the stack. This is when we push the 42 on the stack. This is when we push the return address on the stack. Right after we push the return address on the stack, we continue execution in the function, which is starting at location 05. And then we make a copy. So register C is register D. And you can see how register D has a value of FE, and now register C also has a value of FE. And you can mess around with register C all you want, because it really is not the stack pointer. So as long as the stack pointer stays put, the gremlins won't mess up the stuff that we actually need. So now we can move the stack. We can move the clone of the stack pointer, which is register C, up by 1 byte. Retrieve what is at that location, which is a 2A. Now, how do we know it's 2A? Because that's what we put into that location earlier. So when we retrieve, we are also retrieving 2A from the location FF, and that's why register A is now having a content of 2A, which is 42 in base 10. Now, how do we know 2A is 42? Well, it's 2 times 16 plus 10. Okay, that's why we know that 2A in hexadecimal is 42 in decimal. And then it will retrieve the return address, and the return address is stored in register B. We increment the stack pointer, and then we continue execution at location 0A. And that doesn't look good to me, because 0A then goes to 1, 5. That doesn't seem right to me. Oh, wait, hold on a second. I know why. Because 0A is the last instruction of the function, which is the JMP-B instruction, and then it uses whatever is in register B, which is 1, 5, to continue execution, and that's why we end up at location 1, 5. So it would seem this program works just fine, and that should not be a problem. Except there is a problem. The problem is D, register D, the stack pointer, is not back to 0. So you guys are going to go like, oh no, Tack, you made a mistake. Yes, I have one omission, and that was by design, because the question is, where is that extra byte that is still sitting on the stack? Let me go back to the trace first, and I'll ask you this question. What is still sitting on the stack right now? The stack is not empty. That's because there's one entry, there's one thing on the stack that I have not cleaned up after. What is that? What is at location FF that I did not clean up? The 42, the argument. Very good. Okay, so you guys are all getting this. Excellent. So that means when I'm done, using 42, I should probably clean it up. Okay, so this would be the right point to clean it up. To clean it up simply means I'm just going to increment register D, because that's the stack pointer. The stack pointer just needs to go up by one location to basically say, okay, this location here is not in use anymore, and you gremlins can go ahead and mess it up because I don't care. Okay, it's not in use by me anymore. So this increment D is really important to clean up the arguments still sitting on the stack. All right, so just add one more instruction, and this is why I like this script because I can just make one minor little change and run the whole thing again, even though I have to wait a little bit because I'm totally abusing a spreadsheet, because who would use a spreadsheet to make an assembler, right? But the nice thing is, it does make certain other things very easy, because now you can see, oh, okay, so now we can see that the stack pointer is balanced. Okay, everything is actually good now. So if you want to make a copy, now would be a good time to make a copy. Omer is fast. He just captured the TTP-ASM program itself. That works too. Okay, but if you want to make a copy of the entire spreadsheet, that's fine too. All right, so we are almost about to run out of time. Okay, but there's one more concept that is kind of important to go over, now that we understand that parameters are sitting on the stack. So the question is, what if you have multiple parameters? Okay, so let's go ahead and take a look at the I'm just trying to decide what to do. Okay, so we'll go ahead and copy param1.c to param2.c. And then we'll take a look at param2.c. So now the question is, what if I'm not interested in cloning? What if I am interested in, let's just do a summation of two arguments, okay, or two parameters. So we have uint8 underscore t, this is y, and we want to return x plus y. So now when we call clone, we cannot just give it one number, we have to give it like two numbers, okay, 42 and 7. So how do we do this in assembly? That would be the next question. So your lab doesn't really involve needing to know this part, but I'm going to mention it, and then on next Tuesday we'll come back to this program and implement this particular program. But right now I'm just going to give you a preview of how this is going to be organized. So I'm just going to comment here. Actually, I will comment here in main. In TTPSM, push the arguments in reverse order. So in this case, push 7, then push 42. So this really looks weird, right? This is backwards. TAC, why would we do something like this? Okay, we're pushing the last argument first. Why would we do something like that? Well, there are several reasons. One reason is, in the original C language, you can indeed specify a variable number of parameters. In other words, you can specify, okay, we have these mandatory parameters, and then ... after that, to basically means, after this, we can have any number of additional arguments. Well, that's really difficult to get to, right? Because those arguments do not have names. They're not parameters with names. They're simply other things that you have pushed on the stack. That is why we push arguments in a reverse order. So the last argument has the highest address, and then the first argument, which always corresponds to at least one parameter, that is at the lowest address. So now, based on the one argument, the one parameter that you do have access to, that may give you the clue of how many more things you can expect to be pushed on the stack. And as a result, having the arguments arranged in this way, the last argument having the highest address on the stack it makes it possible and even in a certain sense easy to get to the additional stuff that you have pushed on the stack. So I'm just going to give you the syntax of defining that kind of a function. So I'm just going to put a void function here, which is called f, and one parameter is, let's say, uint underscore t. We'll call it x, and then we have dot 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 here. So now, from the perspective of the caller, you are required. Okay, this is required that you have to pass one argument for sure. So you have to say, okay, we have to pass one argument. But after this argument, you can have any other number of arguments. So now you can have 7, 5, 26, and so on and so forth. So the question is, I know how to get to the 12, okay, because it is from the perspective of C, I know how to get to 12 because that's just parameter x. The question is, how do I get to the 7? How do I get to the 4? How do I get to the 16? And the trick to do this, at least in earlier implementations of the C programming language, is you take the address of x. Okay, so you basically say, I take the address of x, and if x as a value is telling you that there are some additional stuff on the stack, then you do some arithmetic on the pointer itself, on the address, to get to the other ones. So this is really ugly stuff. I'm not saying this is normal stuff that you probably would have learned from CISP360. This is some really ugly code using pointers in a very strange way. But I want to bring this up in order to explain why we push the last argument first on the stack so that it ends up with the highest address, and then the first argument ends up with a known address that is accessible from the perspective of the function. So that's all I want to do, is to kind of give you the rationale of why we push the last argument first on the stack. All right, so let's get back to the lab that we have tonight, because I know some people are anxious and go like, do we have a lab tonight? Well, I kind of answered that question earlier already. Yes, we do. So tonight's lab is, okay, keep going. Right here, it's parameters and return value, which is exactly what we talked about in today's lecture, right? So the passcode, I remember distinctly that we have a frame is the passcode. Now the reason why frame is the passcode is the arguments combined with the return address is called a frame, and every invocation of a function has a frame. So that applies to recursion as well. It's just that in the case of a recursion, you would have multiple frames on the stack corresponding to the same function definition. So we'll get to recursive functions maybe next Tuesday, and then we'll be able to see what I mean by that. All right, so let me save and publish so that you guys can get started. There we go. All right, so the time is 56 right now. I'm going to come back in about 10 minutes. So that way, if you do have any questions, you can kind of put it into Discord, and then I will just be answering those questions when I get back. Alrighty. So if I don't see you again, have a nice weekend, and this stuff is not easy, so I would suggest spending some time to go over the material. Alrighty, I'm gonna get out of the voice channel and live stream, and then be back in about 10 minutes to answer questions.